Still, I'm a substitute for Suri for another lecture. So today I'm going to talk about the conditional gradient algorithm, also known as Frank-Wolf algorithm. I will start with a bit of history about this algorithm, and then I'll give you a few examples. Then we discuss the convergence property of this algorithm. And if time permits, I will show you the equivalence between stochastic gradient descent with the block-wise Frank-Wolf. So let's get started. So, sorry. So historically, the linear programming, I'm assuming everyone knows linear programming. So linear programming is first started by Kantorovich in 1969, around that time. So basically what you're trying to do is you have a linear function which you have a vector c, which is known to you, and you have a parameter w, which is not known to you. And you want to minimize with respect to w such that w is non-negative, and you have a linear constraint a w equals b. Okay, so w usually is in a subspace, say Rd. Okay, it doesn't really matter. So you're trying to minimize the linear function with linear constraints. It's a very simple problem. So, but at that time, when you have this linear problem, if you ask this to a mathematician, they will say this is trivial, right? This is just a linear problem. But if you want to solve it, of course, at 1969, we don't have a computer. But still, if you want to solve a large size of this problem, you will run into trouble. And that is why George Danzig designed the simplex algorithm. So this is Danzig. Roughly, I think it's 60s. Let's say 69 or something like that. Yeah, 67. Okay. So the simplex algorithm for the linear programming, right? So, well, for now we know the simplex algorithm runs at exponential time in the worst case, but on average, it's still polynomial time algorithm. So, and it works very well for linear programming. So now we're getting a little bit more ambitious. Instead of solving a linear programming, we're trying to solve a quadratic programming now, right? Just replace the objective with a quadratic. So it's going to be C, it's still a vector, and I have a quadratic function, a P. It's a matrix now. Sorry. I shouldn't write this way. Where's my escape? So instead of a linear function, we have a quadratic function now. The quadratic function is going to be 1/2 the matrix P plus CW, and subject to the same constraints, a linear constraint. AW equals B. So this is a quadratic program. You have linear constraints, you have quadratic objective function. The question is, how do you solve this? Say back into 1947. How do you solve a quadratic programming, given the knowledge that you can solve a linear programming? Well, certainly you cannot use interior point methods because that's in 1980s, right? You cannot fast forward to 1980s. And you cannot use even projective gradient descent. Why? Because Goldstein invented projective gradient descent in 1962. So still, we are in 1947. So still you cannot use project gradient descent. So how can you solve a quadratic programming? Exactly. So we have a quadratic function. We'll just linearize the. Yeah. Well, it's for now. In 21st century, we know just linearize the objective, right? But at the time when optimization, people just started to know what is optimization. It's not so easy to come up with the idea. So anyway, so the idea is to linearize my quadratic function, and then I will solve a linear programming. I arrive at another point, and then I linearize my objective function again, and I solve another linear programming, and iteratively, maybe I will converge to a solution of that. So that's the basic idea of the conditional gradient algorithm, or known as a Frank-Wolf algorithm. So, okay. So the idea is what I call the power of linearization. So this is by Margaret Frank and Philip Wolff at 56. So there is an interview with Margaret Frank in last NIPS. So basically, she was just graduated from, she was a mathematics student. So she went to Princeton with her husband, and she was in the group of Philip Wolff. So Philip Wolff spent a lot of time with George Dandig developing the simplex algorithm. And then they started to try to solve the quadratic programming, but these optimization experts at the time didn't know how to solve the quadratic programming. But the new PhD in mathematics, Margaret Frank, had the idea of linearized objective. And then, but she, of course, she couldn't prove this algorithm converges or not. But Philip Wolff, was able to prove the whole thing essentially. So the idea is you give me a loss function. So instead of quadratic, any convex loss function, I'm going to linearize it at my current point wt, right? And then I'm going to find, so this is just a linearization. It's a linear function of z. I'm going to minimize with respect to z, which z will satisfy this constraint, right? I just have to write z belongs to q. So this is my constraint q. This is the first step, just linearize the objective, and then do this linear minimization. In this case, it's just a linear programming. And in the second case, well, you're optimizing a function with respect to a set, right? You need to remain in a set. You need to be feasible. If you don't want, because this is in 1940s or 50s, we don't know how to do projections. So you cannot jump outside of the region and then project back. This is not possible. So what you can do is, if I'm in a convex set, I'm taking another point from this convex set. How can I, do things without, going outside of the feasible set? You can just do convex combinations between the points, right? So the idea is you just take a convex combination between your previous point wt. So let's say this is my zt. Okay, here you might have multiple solutions because this is a linear problem, right? You minimize the linear function over a convex set. You might have multiple solutions, but for simplicity, I just write equal here instead of this one. Okay. And then you keep doing these two steps: linearize the objective, solve a linear problem, and then take convex combinations. And if your initial point W0 is in the set, and then you take in convex combinations between the points in the set, you'll be remain in this set. So you will have no issue of feasibility. So this is the basic idea of the conditional gradient algorithm. It's called conditional gradient algorithm because you're taking gradients, and because you have these constraints. So it's a minimum condition in this constraint. So it's called conditional gradient. I should mention that this is in the West. So both Margaret Frank and Philip Wolff are in the U.S. In the eastern part of the world, like in particular the Russians, they have similar ideas related to Frank Wolff. In particular, I think there is another paper by Demirakov and some other Russian. They have roughly the same idea. So, I mean, this is a historical reason, when people in the East don't talk much with people in the West. Okay. Yeah?
Why don't we just directly pick ZT? Is that...
Sorry?
Why don't we just directly pick ZT for WT as well?
Oh, just replace the whole thing with ZT? We'll see why that's not so good idea in a moment. Okay? So now let me first give you an example how this works in a... Oh, sorry. I should just go here. And let's see a very small example, a two-dimensional problem. So I'm going to minimize a function which are two variables, a squared plus b plus 1 squared. So a, b are my variables, subject to, say, a is between -1 and 1, b is between, say, 0 and 2. Okay? If I draw a picture, I should have something like -1 here, 1 here, 1, 2. So I have my feasible region here. Right, this is my Q, this is my feasible region, and this is my objective function. I'm trying to minimize this. So if I follow this procedure, what I would do is, say I start with this point, which is 1, 1. Of course, what is the minimum of this problem? Because it's so small. What is the actual minimizer of this problem? 0 minus 1, this is a squared. So a should be 0.
Yeah, 0 and b equals -1.
It's the origin, right? Right? Because if a is 0, this is 0. And here, this is minimized when b is 0. B is between 0 and 2.
Oh.
Right? Yeah. So we know the optimum is here. And it's unique, right? Because this function is actually strongly convex. So it's a unique minimizer. So let's say we start from here. This is my W0. Well, I take a gradient. The gradient is going to be 2 and 6, right? This is my gradient if I take at this point. And then I'm going to do the linear minimization. I'm going to minimize the linear problem subject to the constraint. And if you know, convex analysis, when you minimize the linear function over convex set, the minimizer will be at one of the extreme points, right? You can always choose one of the extreme points to be your minimizer. So the extreme points, you have 4 extreme points here. These 4 points are the extreme points of my feasible set. They cannot be, we cannot get these points by taking convex combinations, essentially. Sorry?
The gradient should be 2, 4. The gradient.
Yeah, you're right. Good. You pay attention. Okay. So if at this point we're going to try to pick one of the 4 corners, okay, find one of the 4 extreme points, and turns out that we're going to pick this one. This is going to be my Z1. This is my W0, and then the next step I'm going to take convex combinations. So this is the convex combination, right? The convex combination in this line. Then it turns out we will need to choose a step size eta. We're going to discuss that later. But for now, let's say we choose some arbitrary eta. We move to here. This is going to be my W1. Okay? And then you take the gradient again, and then you solve the linear minimization. You pick another corner. And this time, if you do the calculation, you will see you're going to pick this one. And then you take the convex combination, and then you move to here. This is your W2. Okay? And so on and so forth. You will zigzag to the true minimizer. So this is sort of an idea of how this algorithm will perform on this extremely small example. Okay, as I said, this objective function is strongly convex. And when you learn the projected gradient algorithm or the proximal gradient algorithm, you know whenever the function is strongly convex, the projected gradient algorithm will converge at the linear rate, right? Instead of a 1 over t or 1 over t squared rate. In fact, if you run your projected gradient on this example, for instance, you can code everything in MATLAB, in a few lines, the projected gradient algorithm will converge in 2 iterations. You'll find the exact minimizer in 2 iterations or 3 iterations, depending on how you initialize. On the other hand, if you run this algorithm on this very simple, strongly convex objective function, it will take you a while, so 100 iterations. And even worse, you will never actually go to this point exactly. You will zigzag into this point asymptotically, but given any finite time, you are not going to be at this point exactly. So this gives us some intuition, this algorithm might not be, very fast. And the reason you can actually see from this example. So this example is actually the hard case for this algorithm. So whenever you apply this algorithm, if you're running into an application that looks like this example, you probably will try, this algorithm will not converge very fast for you. And the idea is this. So why this is a hard case for that algorithm? So you have your feasible set, and you have your corners, right? You have extreme points of this feasible set. If your optimal point, x star, so let's use W, okay? If W star is the minimizer, the true minimizer, is on the boundary of my feasible set, Q, except, the extreme points, say, how do I write extreme points? So Q1, Q2. So here we have 4 extreme points, Q1, Q2, Q3, Q4. So essentially it says if the true minimizer is on the boundary except the extreme points. Here this is in the boundary of my feasible point, of my feasible set, and it's not one of the extreme points. And if your W0 is in the relative interior or the interior of Q, so here if I start from 1, 1, it's in the interior, in relative interior of my feasible set, right? And then, because in each iteration, you're going to pick one of the extreme points. And you're starting from an interior or relative interior, you take an extreme point, and then you take convex combinations. And if this extreme point has a bigger objective than this one, and if you're doing a line search smartly, because this one, you're going to find a point on this line segment, right? And if this one has a bigger objective, then you will choose something exactly between these 2 points. In other words, you will choose the next iterate in the interior of your feasible set. And then in the next iteration, you choose another extreme point. If the same thing happens, if this one has a bigger objective, therefore you will still be in the interior of your feasible set, and so on and so forth. So during the iteration, you will be in the interior of your feasible set all the time, even though we know that the minimizer may happen to be on the boundary. That's why this algorithm will take forever to converge exactly to the minimizer. So this is sort of the hard case.
So is that the reason why you are doing the second step also? So it's like a line search on...
No, the line search won't help you. So we need this when I write down I'll tell you why we need this step when we write down the proof of this thing. Okay?
It at least answers his question of why you don't choose it to be ZT. Because you'll just oscillate between those two corners otherwise.
Yeah. That's one reason. From a mathematics point of view, so we'll write this as, if you write everything as an operator, so you're essentially you're trying to find a fixed point of operator. And we know if your operator is not a contraction, for example, even if it's a non-expansion, if you just naively do fixed point iteration, you may not converge. But if you add this averaging step, in most cases it will. So it's always good to add an averaging step there. The downside is whenever you add an averaging step there, your convergence is going to be slower. But your algorithm will be more stable. For instance, if you don't have this, as he said, you will just oscillate between these extreme points. If you average things, you will not oscillate. It's going to be more stable. Okay. And as a matter of fact, for this example, even though the objective is generally convex, you can prove we converge in terms of the function value at the rate 1/t exactly. So this is both the upper bound and lower bound. You cannot converge faster, and you're not converging slower than that. We'll prove the upper bound, but the lower bound is you need a little bit of calculations.
Yeah, you said about the contraction, right?
Sorry?
You hinted about contraction. Right?
It's not going to, usually when you have this operator, it's not going to be contraction. If it is, you just do a fixed point iteration, you get a linear rate. But most of the case, it's not a contraction. It's at most a non-expansion. So if you just do...
You see this step in stochastic variation as well. So is that the case there as well?
For stochastic gradient...
For example, when you have global parameters and you have local parameters that you estimate in the Tth iteration, you take a similar kind of a convex combination.
Yeah.
Previous iteration.
Yeah, I think so. This is also to stabilize the algorithm, I think, because of the noise, because of the stochastics thing.
I did not know about this contraction.
Yeah, okay. It's standard in fixed point theory. Yeah. I mean, as I said, if everything is a contraction, you don't need to do anything. It's good. But the knife is always not nice to you. It's going to be a
How do you prove that something is a contraction in a fixed point situation?
You take a norm and you prove the maximum eigenvalue is smaller than 1. That's just sort of the general strategy. Okay. Yeah. Okay, so as I need to remind you again, this is, yeah. Okay.
Sorry for interruption.
Yeah.
There's a variation of the Frank-Wolf algorithm that
Yeah.
involves so-called a wait step, which by doing that, they achieve linear rate of convergence under some technical conditions. Is it possible to illustrate that on this very simple example?
Well, as I will show you, the key, in my opinion, the key of the Frank-Wolf algorithm is, you do this linear minimization. And there are ways to prove faster rates. For instance, you can add a quadratic thing here, or you can do, as you said, do a wait step here, or you can, do the fully corrective thing. But none of them is very useful, in my opinion, because they ruin this property. You're not doing a simple linear minimization.
So the wait step do not use any quadratic.
Yeah, they don't, but they have this very weird assumption, like, as I said, for instance, if you say the minimizer is in the interior, then you can actually show it's a linear convergence rate. It's very easy to show, actually, because if it's the interior, you can have a ball, that sort of, as long as you go there, then it's going to be linear rate. But if this assumption, in my opinion, is very strong, because whenever you have a feasible set, it's very likely your minimizer is on the boundary. So as I said, I don't think there is a very natural assumption under which you can prove a faster rate than 1/t. That's my general impression. Yeah. Okay. So here I just want to remind you, even though this is a nice differentiable convex, strongly convex function, still we can only prove 1/t convergence rate. Okay. On this two-dimensional, very, very simple example. And why is the Frank-Wolf algorithm interesting? This is mostly because of sparsity. And this is realized by Clarkson and some people in machine learning. So let's consider another example where we try to minimize, say, a loss function L of x. Well, this could be W. This could be your least squares loss or hinge loss in your SVM problem or whatever. And you have your constraint. So I want sparsity, I put L1 norm here. For simplicity, I just put 1. In general, you can put a parameter there. So for this problem, if we just apply the Frank-Wolf algorithm, what we do, well, we just, as I said, the first step is going to linearize the loss function. And then I pick a z. I just minimize this, subject to z, 1 norm smaller than 1. Okay? This is arc, and this is zt. And from here, immediately you see zt can only have 1 non-zero entry, right? Because the L1 norm ball, if you think about the L1 norm ball, the extreme points only have 1 non-zero entry. Therefore, if you do the first step, you get a zt with at most 1 non-zero entry. And then in the next step, you just do a convex combination, right? And it's almost obvious the number of non-zero entries in your next step is going to be bounded by the number of non-zero entries in the previous step plus 1, right? Because this guy zt has only at most 1 non-zero entry. So you can only increase the number of non-zeros by at most 1. Therefore, if I run the Frank-Wolf algorithm on this particular problem, if I run k steps, if I start from w equals 0, I will have at most k non-zero entries, right? So therefore, I have explicit control of the sparsity of my problem, as long as I do not take too many steps. So this example actually, so this example has been considered by Clarkson in theoretical computer science, and Sharaf-Schwartz, ETL, in machine learning. So this example basically shows you, the Frank-Wolf algorithm or the conditional gradient algorithm is very different from the proximal gradient algorithm. For the proximal gradient algorithm, if you believe my true minimizer is sparse, okay? If my W star is very, very sparse, then in a neighborhood of this W star, many entries of of these points will be very small, right? Because this one have many zeros, therefore in the neighborhood, many components will be very small. And if you converge to this neighborhood, after you converge to this neighborhood, then you have the proximal operator, which will truncate all the small components to 0. So this means if you apply proximal grading algorithm, you will get a lot of zeros. You will get sparsity as long as you enter a neighborhood of your true minimizer. In other words, you can only get many zeros when you do the optimization, a lot of steps. When you go a lot of steps in proximal methods, you'll get a lot of zeros. Well, for this Frank-Wolf algorithm, you get a lot of zeros in the beginning, right? If I only take one step, I only have one non-zero entry. If I took 2 steps, I only have at most 2 non-zero entries. So in the beginning phase of the conditional grading algorithm, you can only have very few non-zero entries. As you go a lot of steps, you'll get more and more. So these two algorithms seem to complement each other. Although as we will see, the conditional gradient is slower than the proximal gradient. So now let's try to prove why this algorithm works, why it makes sense. And the proof is actually quite easy. Okay, so first let's see. Suppose we know nothing about conditional gradient, we know nothing about the Frank-Wolf. How can we come up with the Frank-Wolf algorithm by ourselves? Well, let's consider a general problem. I'm going to minimize a loss function plus a randomizer. Okay, this is a general setup for machine learning applications. And in that L1 norm case, my randomizer is just the indicator of the unit ball, right? It's just the indicator of that unit ball. In general, you could put any randomizer you like. So this is a problem I'm interested in. How can I come up with the Frank-Wolf algorithm? Well, just look at the optimality condition. The optimality condition says 0 belongs to subdifferential. I'm assuming L is differentiable. And I'm assuming the randomizer is convex. Therefore, I can take subdifferential. Right? This means W is a minimizer if and only if this condition holds. Right? Just take the gradient essentially, nothing fancy. And here we need to assume the randomizer is convex. For otherwise, you cannot take the subdifferential. Okay, so far nothing fancy. So the next step is to just manipulate this as what we did for the proximal gradient, right? For the proximal gradient, I will also just write the optimality condition, and then you do a few manipulations, you get the proximal operator. So here we do the same thing. Okay. This is equivalent as belongs to the subdifferential of R of W. Right? Nothing fancy. I just move this differential to the left side and change the sign. Nothing fancy. And then because of R is convex, we know G is in the subdifferential of R if and only if W is in the subdifferential of R, differential conjugate of G. Right? This is equality that we used last time for the proximity operator. So this holds if and only if R is convex. Therefore, this is equivalent as W. So this is essentially my W. This is my G. It's going to be right? Nothing fancy, just apply that. And from here you can see this. What is this? You can treat this as an operator, T of W, right? An abstract operator. You give me W, I'm going to return another vector, which is called T of W. This is just another nonlinear operator. And you can see this is almost a fixed point iteration, right? Well, it's fixed point inclusion instead of equation, because this is inclusion. But if we just ignore the technicality, this is almost a fixed point iteration. And the reason we don't use this fixed point iteration directly is because, as I said, for stability reasons, we need to average these things. So what we do is we do another step. So we have this equivalence. Well, nothing fancy. I just, this W will cancel with this 1, right? And then we multiply eta. So nothing fancy. I just multiply eta and then I move things around. Therefore, if W is a minimizer, if and only if this happens.
So
okay?
Coming back to your earlier assertion,
yeah.
You said that unless it's a contraction, the fixed point would not converge, right? So
if it's a contraction, then if you apply the fixed point iteration, it will always converge at a linear rate.
But
if it's a non-expansion, it might converge, it might not converge. But if you
whether it's a contraction or not, right?
For the proof we are going to show, for the proof I'm going to show you, we do not need the fact that it's a contraction or not. But in general, when you do fixed point iterations, you can only prove if it's a non-expansion. Yeah. So this is a general trick when people use. As long as you have a non-expansion operator, if you do averaging, more likely you're going to converge. So we just arrive at this, nothing actually fancy, right? So this is a fixed point inclusion instead of equation. So now what we do is, well, instead of Wt plus 1, it's going to be 1 minus eta, maybe depending on t, Wt plus eta t of that thing here. I just repeat that. Right? Nothing fancy, we just apply this optimality condition and derive a fixed point iteration. So I should remind you again, R has to be a convex function, okay? If R is not convex, the whole derivation will break down. On the other hand, if L is not convex, it's still fine, as long as you are satisfied with a local minimum or stationary point, okay? Okay. So we have to derive this, and as you'll see, this computation, this whole thing, this abstract thing here, is exactly the first step we solved before. Okay, this corresponds to step 1. The next convex combination is apparent. Okay. So now we just derived the Frank-Wolf vector if we know nothing about it. Okay. So now we're going to prove why this converges and what is the convergence rate if there is any. Okay. So I'm going to use a different approach. Usually when you prove something, you lay down the assumptions or conditions, right? So I'll do something opposite. I will just present the proof, and if we cannot proceed, we put an assumption, okay? That will help you to understand why do you need these assumptions. Okay. So this is my problem. I'm going to minimize a loss function plus a regularizer. The regularizer is convex. And I'm using that step there. So the first step is very standard. So because I'm taking convex combination, this is my Wt plus 1. I just look at L of Wt plus 1 plus R of Wt plus 1. Okay, this is just the function value at the next iterate. Because I linearize things, so maybe I might equal here. Just plug in the iteration. So this is going to be Wt plus eta of Zt minus Wt plus R of Wt plus eta of Zt minus Wt. Okay, I didn't do anything except I rearranged So I WT and then eta t, these two things. Oh, so I call this zeta t. So this thing here. Okay, we didn't do anything, just rearrange the terms. And then the next step, because I linearize this function, right? I'm going to have, because of convexity, t eta t zeta t minus wt. This is something I would like to have. And plus, because the regular is convex, and this is a convex combination between two terms, therefore I can use convexity to have R of wt plus eta t of R of zt. Right? So I would like to have this inequality. But the fact is I cannot. Why? Because this is a linearization of my loss function L. If my loss function L is convex, there is no way I can bound a convex function by a linear function, except when the loss function is itself linear. Right? If you have a convex function, there is no way you can upper bound it by a linear function. On the other hand, you can always lower bound a convex function by a linear function. So this is something I cannot have, but fortunately, if I allow myself some slack, so here I just put a quadratic term on the step size and a constant c. So why can I do this? Well, you have seen the proximal gradient algorithm. In the proximal gradient algorithm, the assumption usually you have is, sorry. Yeah. So assumption usually is the loss function satisfies this condition, called Lipschitz gradient, right? So L of, say, y is going to be smaller than L of x plus the gradient at x, y minus x, plus the Lipschitz constant L, y minus x squared. Right, this is a Lipschitz condition you saw in the proximal gradient angle or the projected gradient angle. Usually you need this condition, right? And the assumption that I needed is very similar to this, except what I did is I wrote this as a constant times the step size. So if I plug in everything, I will have eta squared here. So what I did here is I just treat this whole quadratic term as a constant c. Okay? So instead of using a second order, refined upper bound, I just take a very crude upper bound, where I upper bound the quadratic term by a big constant c. It's going to be big, but it's going to be constant. So this is what I did in that step. And the reason to do that, as you can see, is because once I upper bound this whole quadratic term by a constant, this is a linear function, right? And then linearity is what makes the conditional gradient algorithm powerful. So on the other hand, if you bring the quadratic term with you, you have to deal with the quadratic problem. That's maybe in some situations it's not what you need or what you want. Okay. And just a side remark, I think you have seen it before. This holds if the gradient is L Lipschitz with respect to the dual norm, right? And the reverse condition holds if L is convex. So these are almost equivalent for convex functions.
I still don't understand how the fuck you bound that quadratic term with your constant.
Because
Bounded domain, so you can.
You assume bounded on it.
Yeah, so bounded domain is eta squared.
the quickest way is, as he said, you have a bounded domain. So x, y are in a bounded domain. In general, you don't have to assume the domain is bounded. You can actually, analyze the algorithm and realize, as long as you're making progress, the whole thing will be bounded in a set.
You're saying it's a sub-level set.
Yeah, you're still within the sub-level set.
But this is not necessarily a decent algorithm, unless you do like line search in every step.
it is not necessarily a descent algorithm if you don't do line search, but you can show, you have a bounded compact subneighbor set, and you can inflate that. And you'll say you're always in that inflated.
That's another assumption.
Yeah. Well, I mean, you need some assumptions. Yeah, that I agree. Okay. So this is an assumption, as I need to confess. But let's move on. So from here, things will become easier because what we have to do is just to rearrange things. So what I'm going to do, because this one has a eta, these guys also have eta. So I will just group them. So this is going to be L of WT, and here we have a 1 of RWT, right? So this is just R of WT. I just group them together, and I have a eta T. So I just group everything else. So here I have ZT and the gradient. And here I have R of ZT, right? And I bring eta out. I have something left, which is just WT of the gradient. I have this thing left, R of WT. And I have a quadratic. Right? Hopefully I didn't miss anything. So just do a regrouping of things, nothing fancy. And now what we realize is, what is this? This is very similar to the step here, except now we're considering a general R function instead of an indicator, right? So here, if I replace this with the indicator function of Q, right? Nothing fancy. And then we just replace the indicator with R of W. So R of Z. Right? So this is my first step. In other words, this ZT is obtained by minimizing for all Z, Z plus R of Z. Right? I obtain ZT by doing this minimization, which is exactly the first step of the conditional gradient algorithm. Okay, so because this is the minimum of this whole thing, and here you can see WT, it also fits into this form, right? WT is actually a feeder point of this subproblem. Essentially, this whole thing is going to be smaller than 0, right? Because ZT is the minimum, and WT is just another point. The minimum minus another point can give you a negative number. This is why you can actually see the angle is making progress, because this is the objective of the current WT. This is a negative number, and this is a quadratic term of eta t. So if eta t is really, really, really small, this one is negligible, right? You're going to have this middle term here, which is negative. That's why the objective value of your next iterate is going to be smaller than your objective at the current state, because this thing is negative, and the quadratic term can be ignored when the step size is small. Okay. I think I can just erase this. Some people call this the duality gap. You can actually show this is a gap bounds the primal and dual, but I'm not going to do it in this lecture. So what we're going to do is to use convexity of L. So here we're going to need to assume L is convex. So if L is convex, how can I bound the whole thing here? Well, because L is convex, this is going to be smaller than L of Z it's better if I write this way. So it's going to be a little bit confusing because I'm changing ZT to Z. So Z is just any point you can imagine, you can pick. So I'm claiming the middle bracket is smaller than Z minus WT inner product with the gradient plus R of Z minus R of WT. So I'm changing ZT to any point Z. This is allowed because ZT is chosen as a minimum, right? So if it's minimum, it's smaller than any other point. And this thing here, now we can use convexity, which gives me L of Z minus L of WT. Or lower bounding the loss function by a linear function. Right, then the rest is just the same. So after we do this, we can continue. Therefore, I have the objective value of the last iterate. Here, this is also the objective value of the last iterate multiply eta t. So this is going to be 1 minus eta t times of L of WT plus R of WT. Okay? And I have L of Z, which is going to be eta t times L of Z plus R of Z. And I have a quadratic term. Okay. So Z, to remind you again, Z is just any other point you can imagine. For instance, we can assume there is a minimizer, then Z can be chosen as that minimizer. We're almost there. So now we just subtract this term, subtract this whole thing from the left side and the right side. We just subtract, we'll get L of WT plus 1 plus R of WT plus 1 minus L of Z minus R of Z. Okay? And now I need to subtract from the right-hand side as well. That gives me 1 minus of eta of this thing. And here, and I have a quadratic term. Okay? So you can already see if this is my, the gap, delta t plus 1, this is my gap at time t, right? Essentially, delta t plus 1 is smaller than a constant times delta t plus the quadratic term on the step size. We have arrived at the recursion. Essentially, this is a recursion. And using this recursion, we can bound this delta. And the idea, I will skip some details. The idea is to choose eta t is going to be 2 over t plus 2. Okay? And then you just, you can either use induction or you can just, expand everything and do a little bit of calculation. It will give you delta t is going to be smaller than t plus 2 over c, I think. Maybe we'll have a 2 here as well. So what does this mean? This means for any other point z, the objective of my WT minus 1 is going to be smaller than that plus a constant, which is decreasing to 0 at the rate 1 over t. So we have proved the conditional gradient algorithm converges in terms of the function value at this rate with this particular step size. And of course, sometimes you would like to choose a smarter choice than this 1 over t step size. What you can do is you can go to here. Here you have eta t, you have eta t squared. You can minimize this quadratic with as a function of eta t. This gives you a better choice of eta t. But as I said, in terms of the rate of convergence, you can only slightly improve the constants, but not the rate of convergence. Okay. Yeah.
So the convergence theorem aside, in practice, how do you set eta t? Is it
in practice, how you set eta t? Use this, or do a line search. Yeah, I mean this is just the quadratic function of eta t, one-dimensional quadratic function of eta t. You can easily solve. Eta t must be between 0 and 1. You can easily solve a one-dimensional quadratic with this interval 0 and 1. So that's usually how you choose things. And the nice thing is actually here, I erased that thing. So we need the Lipschitz continuous assumption, right? But if you look at the step size, you don't need that in the step size. In other words, you don't need to estimate the Lipschitz constant. This is very different from the proximal gradient algorithm, where you do have to have an estimate of the Lipschitz constant. Right? You cannot have a very too small step size. And here it's actually independent. I mean, if you have an estimate of the Lipschitz constant, you should probably multiply that. That will improve the constants. If you don't have an estimate of that, you can just use this, and you can maybe influence the constant a little bit. And the other thing is, this conditional gradient algorithm is sort of adaptive in the sense of when you use a proximal gradient algorithm, you need to assume my function is Lipschitz continuous, my gradient is Lipschitz continuous with respect to some norm, right? It could be any norm, but you need to pick a norm. You need to commit to that norm. Because when you compute the proximity operator, you have to use that norm, right? You need to commit yourself to that particular norm. Here, for the conditional gradient algorithm, it doesn't matter which norm. All you need is the existence of such a norm so that my gradient is Lipschitz continuous with respect to that. As for which norm or what kind of norm, the algorithm doesn't care. So you don't need to use this. And in a sense, the algorithm itself is adaptive to that. Okay. So, any questions about the proof? Yeah.
Does this require a bounded domain?
Yeah, it does. The easiest way is to assume you have a bounded domain. A slightly more fancier way is to see it from here. So if eta t is chosen smartly, you're actually decreasing the objective function. So as long as you have the level set is bounded, you will remain in that level set. In other words, you will remain in a bounded set.
If you're doing line search, you choose z though, shouldn't that be unbounded?
Yeah. Yeah, that's a problem. So this is actually a problem I hide. So here it's essentially in this step, in the first step here. So in this first step, there is an issue. So if this is a bounded Q, then there is no problem, right? I'm minimizing a linear function over a bounded set. There is no issue. But if I replace this indicator function with a regularizer, for instance, if it's a norm, let's say it's the L1 norm, or the L2 norm, or whatever norm you like, this is essentially a linear growth function with no constraints at all. You're minimizing a linear growth function, something might go wrong, right? It might converge to minus infinity. So this is an issue. A fix that we did, I think, in the last NIPS is very trivial. What you do is, for instance, if I have L1 norm here, so this one can diverge to minus infinity. What I do is I truncate the L1. So I put a constraint, say the L1 norm is bounded by 1. Okay, this is a very artificial truncation. And I just pick an arbitrary number 1 here to make sure this first step can be executed. And because I choose a bounded domain, this might affect my convergence. Therefore, when I pick the step size, eta t, I need to compensate for this choice. So what I do is I introduce a line search over the essentially a line search over the step size, and then because of the norm is homogeneous, then you can actually show the whole thing still works. So essentially, whenever you have unbounded domain, you just pick and L1 norm, and you restrict yourself to that bounded set, and then you do a line search over the step size to compensate. So this is sort of a general idea, yeah.
It is interesting that this fix we use is actually used by Martin and Wright when they try to prove the linear convergence rate to the statistical accuracy. They also add a similar like norm bound of the regular address that is large enough, and it gives you like it controls the initial steps to make it to allow the algorithm to constrain itself within certain region instead of going all the way to very far.
Yeah, I see.
Away. So that actually gives you the linear rate
for the proximal one, yeah.
Yeah, for
I
the
see.
proximal operator.
Interesting. Yeah, I see. Okay. Yeah. So we use essentially the same idea. We just constrain ourselves and then do a line search to compensate. And it's quite surprising that this simple naive thing seems to actually works.
So,
Yeah.
Usually you do a line search only like for the convex combination.
Yeah.
A line search will have to account for that. Right? It have to be further also.
No, when you do the line search for the convex combination.
No, I'm saying in your altered method.
Yeah.
Do you have to do a line search beyond the convex combination?
Yeah. So essentially from 0 to infinity, the line search.
Right. So how do you do that?
Well, it's a one-dimensional problem. Yeah, it's a one-dimensional problem.
So you basically just use Z to estimate the direction and then.
Exactly. Because this is a norm. So you can just fix the array and then try to find the scale.
Right.
That's the basic idea. I mean, it's almost sounds like trivial, but anyway, okay. So now you have this conditional gradient algorithm. You have the proximal gradient algorithm. Which one should you use in practice? Well, as I said, the conditional gradient algorithm is slow because it has a rate of 1 over t, and this 1 over t rate is actually quite tight in many applications. On the other hand, the proximal gradient algorithm, if you use the acceleration, you'll get 1 over t squared convergence rate. And in practice, you usually get a much faster rate than that. So it seems like the conditional gradient has no use. However, the beauty of conditional gradient is in the linearization. So in each iteration, you only need to solve the linearized problem instead of a quadratic thing. So in proximal gradient, you need to solve a quadratic problem. This sometimes may make a difference. So I'll show you an example, which you probably have heard of before. This is my convergence proof. I don't want to ruin that. Yes. So this is a trace norm regularized problem, right? So you have a matrix completion problem. You have a sampling operator A with a matrix X, and you have your observation. So this is my W. X is my observation. Forbidden norm squared plus the trace norm. And here we have W. So as I said, if you use this formulation, when you solve the subproblem, you need to constrain yourself. Okay. So for this problem, if you use the projected gradient algorithm or the proximal algorithm, you need to compute the proximal operator of the trace norm. The proximal operator of the trace norm is not hard to compute. All you need to do is to compute a singular value decomposition, right, on the matrix, and then you truncate the singular values, right? And the downside is when the matrix is huge, you need to compute the full SVD of this huge matrix and get all the singular values and then look, which one is small, which one is big. If it's small, I just truncate to 0. If it's big, I just, minus some constant. There are some tricks to accelerate that. For instance, maybe you can compute 10% of the singular values. And then if the smallest one is already small, then you don't need to compute the rest, right? If the smallest one is big, then you compute the next 10%. So tricks like this, people have tried. But still, if your matrix is huge, this 10% or, can still be very expensive. On the other hand, if you apply the conditional gradient algorithm to this problem, the sub-problem, the first step, what you need to do is to minimize the gradient of this, which I just denote as delta L of W. This is a matrix now. And you have T, matrix Z, subject to the constraint Z, trace norm is smaller than 1, right? This is the first step essentially here. So I should write the trace norm as a sum here, but as I said, this is a linear problem. If you have a trace norm, you will diverge to minus infinity. That's why we restrict ourselves. So we just have this trace norm smaller than 1. What is this? Well, this is nothing but the spectral norm. Oops. It's getting smaller and smaller. The spectral norm of the matrix. In other words, instead of computing the full SVD of this gradient matrix, all you need to do is to compute the maximum singular vector or maximum singular value of your gradient matrix. So instead of computing all, you only need to compute one of them. And this makes an order of magnitude difference. So for this problem. Okay?
Are you missing a negative there?
Yeah, I do. Yeah, right. I don't have a, yes, yeah. Yeah, I do missing a, and I should write spectral norm instead of 2. 2 is more confusing. Okay, I have 15 minutes. What should I do? I can give you one more example. Or, okay, maybe I'll show you the equivalence between stochastic gradient descent in the primal and the conditional gradient in the dual. Okay, they are almost exactly the same. But before that, I need to mention, so as I said before, so when you have a norm here, you restrict yourself and you do a line search. This seems to be a very naive idea. As a matter of fact, if you think about the adder boosting algorithm, the boosting algorithm, what they try to do is to minimize the exponential loss of your data, right? And then try to find a convex combination of weak classifiers. You can actually obtain the adder boosting algorithm exactly in the form of this algorithm by using this symbol, by writing out the loss function is the exponential loss plus 0 times L1 norm, okay, which is nothing. But if you write it this way, and then you specialize everything to this conditional gradient algorithm, you will actually recover the exact form of adder boost, which is a very interesting thing to observe. Okay, I don't have time to go to the details. Just a minute. Yeah. Sorry?
Can you put that in? What you said, 0 times the adder loss of?
0 times L1 norm. So essentially, adder boost tries to minimize the exponential loss, the sum of exponential loss of your data, and a convex combination of your hypothesis. Sorry. Right? And how do you do that? Well, they are taking essentially a coordinate descent step. So what I'm saying is, if you just pretend you have a regularizer on this W, which is just 0 times 1 norm, okay? This is exactly the same, right? But just pretend this is a non-zero number, and then just do the conditional gradient step. And then just derive the first step, derive the convex combination, do a line search exactly. Because this is exponential function is nice, you can do the line search exactly. And if you do all the steps, and at the end of the day, you get exactly the adder boost algorithm.
In this raises the question, why on Earth we need to use 0 here? Why not something else?
Exactly. You can change 0 to be some lambda to regularize yourself. And in fact, the line search thing we came up with is, the motivation is actually to do adder boost with L1 regularization, essentially. Okay. So in the remaining 10 minutes, we'll give you a very high-level explanation of the primal, of the equivalence between stochastic gradient descent and randomized Frank-Wolf. Or maybe I'll just do the easy one, not the stochastic one. So again, the problem is minimize LW plus R of W. So you can have many algorithms to solve this problem. This is a primal problem, right? You can use gradient descent. If the function is non-smooth, you can use subgradient descent. Just take a subgradient and keep doing the gradient steps. What is the dual of this? Well, I need a better thing. Okay. There are many ways to derive the dual, and in particular, I'm going to use the so-called Fenchel, the Rockefeller-Fenchel dual, which essentially says to minimize this is equivalent to minus minimize. I use alpha because it's more familiar to some people. L star, the Fenchel conjugate, R star, the Fenchel conjugate of alpha. Okay, these two are equivalent. A quick way to derive this is, this one is mean of W. I just write the definition of the Fenchel conjugate, which is sup over alpha W minus L star of alpha plus R of W. And then you swap mean and sup, which is unjustified. You need to justify that. If you just swap, assuming it's equivalent, mean of W, and then you get alpha W plus R of W plus L star of alpha. And this, if you change the sign, this will become max, and this will be R star of alpha. And then you move minus sign out, you get the minimizer. So that's a quick way to derive the Rockefeller dual. But of course, everything hinges on, the ability to actually swap the min and the max, which I'm not going to justify here. Okay. So now you have a primal problem, you have a dual problem. And the assumption is, so this time I need to explicitly say that R is strongly convex and differentiable. This is a technicality, but it's okay if it's not differentiable, but you need to pay some extra care. So if, for instance, R of W is going to be 2 lambda 2 norm squared, right? This is the usual one. Okay, this is the assumption. And from here, because this is strongly convex, you can actually see its dual, its Fenchel dual, is going to be a smooth function. So this one is going to be a smooth function. You can pretend this is your loss, L tilde, and you can pretend this is my regularizer, R tilde. Okay? So in the dual, you swap the meaning of loss and regularizer. The Fenchel dual of the regularizer now becomes a loss. And the Fenchel dual of the loss now becomes a regularizer. And the reason to do this is because we assume the regularizer is strongly convex. Therefore, its dual, its Fenchel conjugate, is going to be a smooth function. And in order to apply the conditional gradient algorithm, we need the loss function to be smooth. That's why we change the meaning. This one now is a loss function. So you can apply the conditional gradient algorithm in the dual. What you'll get is, in each step, you're going to take a gradient of your loss, which is the Fenchel conjugate of the regularizer, and you're going to find a beta and you have a regularizer, right, which is the Fenchel conjugate of your original loss. This is the first step you do, and then the next step, sorry, I should put the T. This is the beta. And then in the next step, you just do a convex combination. Nothing fancy, as usual. So this is a conditional gradient in the dual. Okay, nothing fancy, we just apply what we have learned. And for the primal, what do? Usually, when you apply the subgradient algorithm, what you do is you have Wt plus 1, which is going to be Wt minus a step size eta t times the subgradient of L at the point and the subgradient of R, right? Because R is differentiable, it's an assumption. I just write R of Wt. So this is the subgradient in the primal, okay? Unfortunately, these two are not exactly equivalent, and the tweak you need is actually something quite weird. So these two are not equivalent as I hinted. But there is a variant of the subgradient algorithm, which makes the conditional gradient in the dual going to be exactly the same as the variant of subgradient in the primal. And the variant you need is this. So instead of doing this update, what you are going to do is Wt plus 1 is going to be the argmin of W. Here is my W. And here's my subgradient. Plus the quadratic term. The quadratic term turns out to be the Bregman divergence induced by R. Because Rw minus R of Wt minus W minus Wt delta R of Wt. Okay? If R is this thing here, this is exactly that. Okay? So if R is the square norm of the L2 norm, the Wt plus 1 of this weird stuff is going to be exactly that. But in general, you can use any other strongly convex R, and then these two are not going to be equivalent anymore. And you can prove the primal if you do this update in the primal, and if you do the update, this update in the dual, then I think I need to check. I have 4 minutes. Yeah. Then by identifying W as alpha, by doing this identification, so W is going to be the gradient of the French conjugate of R at alpha. These two will become exactly the same. Okay, so I'm skipping some mathematical details, but you can do the calculation. Essentially, you just derive the optimality condition here, and then you derive the optimality condition there, and you can see under this identification, these two optimality conditions are exactly the same. So this observation is first made, I think, in a paper by Francis Bach. I think it's last year. And another almost immediate observation is if my north L is in the form of sum. So I have n data points. I should have my loss is going to be in this form, right? I just sum over the losses of every data point. And now here, instead of having alpha, you have for each data point, you have a dual variable alpha I. So you have essentially a bunch of these alpha i's. So this is going to be the sum, I think. Something like that. And then if you're doing stochastic gradient descent here, so in each step, you randomly draw a data point. And then you do this weird subgradient step. This is going to be equivalent as in the dual. You're going to have these blocks of these alphas. You randomly draw a block of this alpha, and then you do a conditional gradient on that block E. So these two will become exactly equivalent. I mean, the proof is exactly the same as the non-stochastic thing. And the block-wise conditional gradient is done also last year, I think, by Simon and Jaggi. and Schmidt, and some other guy, I think it's Pletcher or something like that, ICMO last year.
What are the blocks of alpha correspond to?
So for each, so essentially, if you remember, how do I get the dual? Essentially, I'm just writing out the function conjugate of my loss, right? Here, for each individual loss Li, you introduce a dual variable alpha I. So essentially, what you do is you write Li of W as sup alpha I W minus Li star of alpha I. So that's how you get, for each data point, you get itself alpha I. So for each data point, you get a dual variable, which is a vector. Okay, it's not a scalar. So you have this equivalence. And again, here, this assumption, this strongly convex assumption, you can remove that using the idea of smoothing. As we talked about last time, whenever you have a non-smooth function, you can replace that with the Moreau envelope. You get a smooth function. So if you do this, you can actually show the equivalence between the regularized dual averaging, which is another method, with the equivalence of the conditional gradient. So there are a bunch of these equivalences. So that one I think has not been explicitly stated. I mentioned that in my thesis, but I think so. The conclusion is, or the message is, there are so many algorithms, like subgrading algorithms, conditional gradient algorithms, but many of them are actually equivalent. They're just, if you do the math carefully and you do the identification carefully, you can actually see there are not so many, actually. So many of them are just equivalent. Yeah, I think I'm running out of time. I just stop here.